Welcome. Today we will be discussing section 2.6. Topics include one-to-one functions, inverse functions, and complement formula. For a one-to-one function, the definition is as follows. We'll have some function f and some set d. We'll say that the function is one-to-one whenever we have x1, x2 are in D, and f of x1 does not equal f of x2 when x1 does not equal x2. In other words, if we have two different inputs, we're guaranteed to have two different outputs. So why do we care about this? Well, we can have a restricted inverse function. And what that does is we're going to say that f is one-to-one on some set D. And for every x in D, if f of x equals y, then define G such that G of y equals x. So in other words, wherever this function sends a element to another element, this function G is able to send it back. And if it is on the entire domain, that is if D is equal to the domain of f, then G is the inverse function of f, and we would denote this as f to the negative first, or f inverse. That is G. So we can think of that as another way of describing it. So essentially what it is that with the restricted inverse, we're going to take a part of the domain and say that we can map a certain part of it back to itself. Here, we're saying that the entire domain, we can recover our x. We can go back to the original input. Now, with this, we have some properties for an inverse. And what we have is the domain of f is equal to the range of f inverse. The range of f is equal to the domain of f inverse. We will also get that f of g of x, or this would be of y, is equal to y, and g of f of x is equal to x. Meaning, if I start with an element by applying the restricted inverse and then the function, I'm going to get my element back, or whatever my input element was. And this works for either case, as long as I'm consistent from where I'm pulling it from. So x is within the domain of f, y is within the domain of g, or we could also think of y being in the range of f. Again, what's important to note is that the restricted inverse is when we just have a piece of the domain, and an inverse is when D is the domain. That's everything. So the entire function is one-to-one. Okay, so how is this useful? Well, we can define an inverse to our trig functions. So inverse sine what we can do is we're going to call it arcsine, or we can call it sine to the negative first. Now, I prefer the term arcsine. You can use a sine to the negative first. It's probably what your calculators have. And the reason being that we know this isn't sine to the power of -1 is because we could just simplify that as cosecant. So whenever you see sine to the negative first, you should be thinking sine inverse, much like the inverse function notation, versus sine to the power of -1. So what does this entail? Well, we know sine of x equals y. So we have to look at what our domain and what our range is. And so in this, we know that y is somewhere between -1 and 1. But our x, it can take any input and it repeats. So we're going to take just a section of the sine graph and make a restricted domain. So we're going to take x to be somewhere between -pi/2 and pi/2. So now, if this is our restricted domain, this is our range for sine, we're going to take the inverse of it and say that the domain for sine inverse is -1 to 1. And the range for sine inverse is -pi/2 to pi/2, inclusive. And so we do this because we can create a one-to-one function on this domain for x in terms for sine. And now sine inverse can map any element from sine and basically undoes sine back to itself. So what does this mean? Well, we have some properties. We have that sine of arcsine of x is equal to x. And this is when x is within somewhere between -1 and 1. That's what this means is in. So it doesn't make sense if x was like -2 because that's something that was never in the range of sine. So we'd have to put in something with a value of between -1 and 1. Now, arcsine of sine of x. So now sine is the first function, and then we apply arcsine, and we get, or let's use theta instead and make it different. We get theta again. However, theta must be within -pi/2 to pi/2. And so let's do a quick example of how we could get something a little bit different here. Say if I had arcsine of sine of 2 pi. It might be easy just to say 2 pi here. However, that isn't within the range of this function of arcsine. So instead, we'd have to use a formula and say, okay, well, if this is 2 pi, sine of 2 pi, what is an equivalent statement? An equivalent statement would be arcsine of sine of 0. Because sine of 2 pi is 0, sine of 0 is 0, and now 0 is within our function, and so we can state 0. So note that 2 pi is not the answer to this question. It might seem natural to put that answer, but we have to be within the range specified by the inverse function here. So let's find a more concrete example. We want to find the exact value of cosine of sine inverse of -1/3. So we can't simply just write down -1/3 because we have cosine here and not sine. So we have to make it in terms of sine. Well, we could do it the following way. We can say, all right, well, this arcsine, let's focus it on that. Or sine inverse of -1/3. This is the result of sine of some theta that is equal to -1/3. Or basically pulling out that sine and saying, okay, what angle would get us this? And more specifically, what angle would get us this that is within our range of -pi/2 to pi/2. So it's negative, so we must be somewhere in this fourth quadrant. Why? Because here this is pi/2 for our theta, and this would be -pi/2 if we're going this way. So -pi/2. So we're working somewhere on this half of the coordinate system. Okay. So since it's sine theta is -1/3, then we can write -1, 3. So we have -1 here. We're going down 1. And then here we have a hypotenuse of 3. And here is our theta, our reference angle. Well, how can we find the cosine? Well, the cosine is adjacent over hypotenuse, so we need to know what our x is here. So we can go with Pythagorean theorem and say 3 squared is equal to -1 squared plus x squared. So that is 9 is equal to 1 plus x squared. This gets us 8 is equal to x squared. Take the square roots. And we get 2 square root 2 is equal to x. And how I got this is that I split this 8 into 2 times 4. Square root of 4 is 2. And that 2 is times by what's left in the radical, so 2. Leaving us with 2 square root 2 is equal to x. So our cosine of this angle theta, so cosine of theta is 2 square root 2 over 3. Now, the last question we should ask ourselves is this x positive or negative? Because we could have gotten either. And we're in the fourth quadrant, so cosine is positive. Therefore, we leave this being positive. And that is our answer. We get 2 square root 2 all over 3. Oh. So now we could introduce inverse cosine. And it will run much of the same way. So let's erase this and see what we have for this function. Inverse cosine, we can denote this as arc cosine. Sometimes we'll abbreviate it to arc cos or COS. We'll also put it as cosine inverse. And we know that cosine of some theta is equal to some x value. And now we will describe that what the range and domain of cosine is. So the domain, again, is all reals for cosine, but we're going to instead focus that the domain for cosine inverse is, again, -1 to 1. Because that is the range of this x. So this x is somewhere between -1 and 1. Now, we have to find a portion of the domain of cosine that gets us this range of -1 to 1. And if we use the same domain as sine, notice the cosine is the x variable in terms of a point here, and we just have it be positive the entire time. So we need somehow to include the other side of the axis, and so we end up using a domain that can go both in the first quadrant and the second quadrant, meaning that our theta is somewhere between 0 and pi. So that means our range for cosine inverse is 0, pi. Okay, and this is the important takeaway. Our properties will rely on much of the same, that this time we have cosine inverse of some value theta, or let's do x. We'll get it right back. And in a very similar stance, arc cosine of theta equals theta, but we have to attach that theta must be within 0 to 2 pi. Or sorry, 0 to pi. Okay, so what's easy about this one is if we don't have an x that's within our range of our original function, that being -1 and 1. So if it's not within the range of cosine, it's just an invalid input. So again, something like 2, -2, -10, it's just not a valid input because cosine could have never gotten there to begin with. Whereas here, cosine of 4 pi is an answer. We can get whatever that is, which is 1. However, arc cosine, when it receives a 1 as an input, it says, okay, how do I obtain this? Well, I can obtain that when theta equals 0. It doesn't see the repetition that cosine is able to get to. So important consequence of these two theorems, or definitions, I should say, is how cosine and sine behave. If we have sine, this is the complement formula, if we have sine inverse of some value and cosine inverse of some value, we know that's going to equal pi over 2. And this is when x is within -1 to 1. Okay. So how can I state this with such confidence? Well, we could see this through a variety of methods, but if we have some input here, so let's bring back our triangle that we originally had, where we had -1, 3, and 2 square root 2. What ends up happening is this value of -1/3, so this triangle was a result of x equaling -1/3. Sine inverse would get us this angle here of -1/3. Well, how do we get cosine of the same 1/3 or -1/3 to get us another angle? Well, it's adjacent over hypotenuse. So if we reference beta here, now it's adjacent over hypotenuse to get -1/3. Where here, theta gets us opposite over hypotenuse, which is -1/3. And so we have our theta plus beta, and we know that that must be pi over 2 because the triangle is 180 degrees or pi radians, and we have a right triangle here, so we have pi over 2, so there must be pi over 2 between these two angles. So if we add them together, we get pi over 2. What does this mean? Well, it allows us to answer questions like this. We want to find the exact value of following. So find exact value of sine inverse of -1/2 and cosine inverse of -1/2. Well, we can simply take which one would be easier to solve. And you might look at this and go, I don't know. Well, in that case, just pick one. And we can find the other one as a consequence of one that we do solve for. What do I mean by this? Well, we can take sine inverse of -1/2, and we know that that's equal to some theta. Okay, so we can say that sine of some theta is equal to -1/2. We then can use this property to go, all right, we have a triangle of -1 and has a hypotenuse of 2. So when we do that, what triangle can get us this? Well, that is a pi over 6 or -pi over 6. So theta is equal to -pi over 6. Okay, well, if theta is pi over 6 and we have this identity up here, we can then state that cosine inverse of x must equal pi over 2, and we're going to subtract this answer. So we're going to minus a negative pi over 6. So we're going to add a pi over 6. And to get same denominators, I'm going to have 3 pi over 6 plus pi over 6. And that gets us 7 pi over 6. So, oh, sorry, 4 pi over 6. That was dumb. Which I can reduce to 2 pi over 3. So I can rewrite this as sine inverse of -1/2 is equal to -pi over 6, and cosine inverse of -1/2 is equal to 2 pi over 3. And that is my answer. Notice I constructed one of the triangles and I constructed it in the quadrant that was in the domain of sine. I didn't have to second guess if this triangle in the fourth quadrant was an angle to consider because we're restricted to the first and fourth quadrant for sine inverse. And we can check this answer as well and see that this answer of 2 pi over 3, that answer lies within the second quadrant, which is all right because the cosine domain is within the first and second quadrant. Okay, so that is the inverse functions, one-on-one functions for your check on learning. It will be to write down the complement formula, as well as write down the domain and range of inverse cosine and inverse sine. Thank you for watching and have a great day.